Welcome back, everybody. Today we're going to get started talking about polynomials. Polynomials are extremely important on your way to calculus because they have certain properties that if you can identify it's a polynomial, you can count on these properties to make problems a whole lot easier. All right, so the first thing we need to do is define what a polynomial is. Now, there is a very mathy definition in your book, probably. I like to break it down by first what a monomial is. And then what a polynomial is, all right? So a monomial is a term comprised of a variable, a coefficient, and a non-negative integer exponent. So it's comprised of a variable, a coefficient, and a non-negative integer exponent. All right, so that is what a monomial is. It's a single term comprised of a variable, a coefficient, and a non-negative integer exponent. All right, a polynomial is a collection of many monomials. So, for example, 3x cubed is a monomial. 2x is a monomial. 3y squared is a monomial. If I string them together, I get a polynomial. All right, so what we're going to do now is we're going to talk about if it's a polynomial or not. All right, I have a couple of examples that we're going to do. So the first one is f of x equals 3x minus 4x cubed plus 8. And the question is whether it is a polynomial or not. So you look at this, and the only question I have for you is does it fit the definition? It does. Now, this is not normally the way you would write this polynomial. If you were writing this polynomial, you would write negative 4x cubed plus 3x plus 8. But even out of order, you would say that, yes, this is a polynomial. All right, so normally we write it in descending order of exponent, but even if it's not in descending order of exponent, it doesn't change the fact that it is indeed a polynomial. All right, the next one's kind of interesting. Just 5. So I want you to pause for a second, think about it. Does this fit the definition? Now, I usually in class get mixed reviews. Some say yes, some say no. But what if I rewrote it like this? Did I change the polynomial? Or, well, okay, I gave you the answer. It is a polynomial. Did I change the expression? The answer is no. All I did was make your variable visible to the naked eye, right? Because x to the 0 right here equals 1. 1 times 5 is just plain old 5. So even though 5 is a constant, there is a variable in there, just its power is 0. So you would say, again, yes, this is a polynomial. All right. Now I'm going to give you one more. All right. So how about this? The question is, does it fit the definition? Are each one of these monomials have a coefficient, a variable, and a non-negative integer exponent? And even though it looks like it might, if you wrote it as a string like that, you would see that that x in the denominator actually is an exponent of -1. So in this case, this does not fit the definition, hence, no, it is not a polynomial. All right. So there are many more examples that we can do, but let's talk about the advantages of knowing it's a polynomial. All right. And I said there were certain properties that you can count on if you can identify it is indeed a polynomial. The first one is the domain of any polynomial is all real numbers. All right, domain is kind of the white whale of pre-calculus, and it comes in very handy in calculus if you're pretty good at it. But let's look at our not polynomial here. Is this domain all real numbers? The answer is no, because if x were to equal 0, right, the 4 over x would be a problem. So even if you thought, yes, this is a polynomial, you could say, wait, the domain is not all real numbers, hence it can't be a polynomial. All right. The next property is the graph of a polynomial is a continuous curve. This stems from the domain being all real numbers. If the domain's all real numbers, that means there's no breaks in our graph. Hence, the graph is continuous. The last one, which you'll hear more about this term, but the graph of a polynomial is a smooth curve. That means that there's no sharp corners, there's no quick turns, there's nothing that looks like that in it. All right, and that makes a huge difference when you get to calculus and you start talking about things like derivatives and integrals, because unless your function is continuous over the interval, right, which means the domain doesn't break and it's a smooth curve, right, you won't be able to do those more advanced things. So it's very important that you recognize. All right, so now that we've talked about what a polynomial is, let's talk about some aspects that we maybe have discussed before. And the first one, right, that we've discussed before is x-intercepts. There's another term for x-intercepts that you're going to see here. You might have seen it before, you might not have, and the term is zeros. The reason it's called zeros, it's because where y equals 0. So for example, I can say f of x equals x to the 4th minus 2x cubed minus 3x squared. Find the zeros of the function. Basically, I'm saying find the x-intercepts. So how would I do this? I would take x to the 4th minus 2x cubed minus 3x squared. I would set it equal to 0, and now we'd look to solve this. So in each one of my terms, I have a common factor of x squared, so I'm going to pull that out. And I'm left with x squared minus 2x minus 3, right? And then I can factor x squared minus 2x minus 3 to x minus 3, x plus 1. And now I want to solve all three of these terms, because if any one of these terms equals 0, all of them equal 0. So x squared equals 0, x minus 3 equals 0, x plus 1 equals 0. So x equals 0, x equals 3, or x equals -1. So in this particular function, which started out with x to the 4th, we have 3 real zeros. or 3 x-intercepts. You can use those terms interchangeably. It all depends on what you're given. All right. Now I want to try the problem backwards. What if I were to give you the zeros and the degree? So find a polynomial of degree 3 whose zeros are -4, -2, and 3. Now, the first thing I want to talk about is what the degree is. So let's go back up to our other example. The highest power on our variable is the degree of the polynomial. That's why we write them in descending order, because our leading term holds the degree. So in this particular polynomial, the degree is 4. In this particular problem, I'm looking for a polynomial of degree 3. All right? So in a sense, I want to do this problem backwards. So I'm going to start with, right, I ended with x equals 0, x equals 3, x equals 1 in the previous problem. I want to start with, let's go back to a pen. That'll be much, much easier. X equals -4, x equals -2, x equals 3. All right, and then I go to the next step up, and I see that I had everything on one side and the whole thing equaling 0. So I'm going to scroll up for a little more room. I'm going to add 4. I'm going to say x plus 4 equals 0, x plus 2 equals 0, x minus 3 equals 0. And now each one of these was a factor, and the whole thing equaled 0. So we're working our way back up to that string polynomial that we had before. So now let's FOIL the first two. So I get x squared plus 6x plus 8 times x minus 3 equals 0. And now we basically have to use distributive property to get the last little bit. So I'm going to take this x and I'm going to multiply it times my trinomial. So basically what I'm going to do is, rather than try to do it in my head, I'm going to write it out. I definitely endorse writing it out. All right. It's one more line of writing. It's not necessarily more work because you're only writing out what you're going to do. You're not actually doing anything just yet. So now I'm going to take the -3 and I'm going to multiply it times x squared plus 6x plus 8. And the whole thing still equals 0. So I only wrote out what I'm going to do. I didn't actually do anything just yet. So now let's do it. All right. So, but it's much easier to distribute one term than two terms. So I get x cubed plus 6x squared plus 8x minus 3x squared minus 18x minus 24 equals 0. Now, the last piece of this is we basically need to just get our like terms together. So I have an x cubed. It's the only one I have. So now what I'm going to do, I'm going to use my highlighter so I can still see it, but I am going to cross it out. All right, so I have 6x squared minus 3x squared is positive 3x squared. And again, I'm going to cross these out, because as I cross them out, if I have anything left, I know I might have missed something. So now we're looking at 8x minus 18x is minus 10x. I'm going to cross these two out. And then minus 24. All right, and everything is crossed out, so I didn't miss anything. And this is a polynomial. Its degree is 3. And we know that when we started, what our zeros were. So hence the problem is complete. All right. So there are some theorems that go with polynomials, one of which that you will explore more in calculus, but I'll introduce it to you now, is the intermediate value theorem. Okay, and the intermediate value theorem says, suppose f is a continuous function between a and b. All right, if f of a and f of b have different signs, there is some place in between, they called it c, where f of c equals 0. All right, most likely it's written in your book. So, for example, if up here I have a f of a, and down here is, actually, you know what? I'll do this a little bit better. And over here is, hang on, b f of b. All right. And if this function is continuous on this in this interval, it has to go below the axis at least once in order to get to b. So basically there is some number c, right? There could be more than one. In this case, the way I drew the graph, there is 3, where f of c equals 0. All right, so let's try an example. Show that the function f of x equals negative 2x cubed plus 4x plus 5 has at least one real 0 between 1 and 2. All right. So the intermediate value theorem says, first things first, the function has to be continuous. Well, I look at my function. The only thing I have to decide is it a polynomial? If it's a polynomial, I know it's continuous. I don't have to worry about that. All right, I look at the function. It is a polynomial. I know it's continuous. So basically what I need to know is I need to know f of 1 and I need to know f of 2. So why don't you pause the video now, evaluate f of 1 and f of 2, and we'll talk about the answers on the back end. All right, so for f of 1, I got 7, and for f of 2, I got negative 3. All right, so now, by the intermediate value theorem, I just prove this. Now I want to show you why that this is proven. All right, so if I quickly make a graph and I go 1, let's call that 7, and I go 2, we'll call that negative 3. Right? These are just 2 points on the function, but the function is continuous, which means that basically it has to go through the x-axis and create a real 0 somewhere in there. I don't know if this is the graph. It could be the graph. It could go up, down, up, down, up, down 12 times for all I know. But all I needed to prove was there is at least one real zero. And this, I could say, and I have to invoke the theorem if I want to use it, by IVT, intermediate value theorem. IVT is an acceptable abbreviation. There is at least one real zero between 1 and 2. Okay. So now I want to talk about end behavior. Now with polynomials, again, we go out to infinity. So end behavior basically talks about what happens as x goes to infinity. All right. So if I'm saying as x goes to infinity, the mathematical symbol for that would be like this. Saying x, this would be goes to infinity. All right. And basically, for right now, we're going to classify end behavior into 4 categories. All right. Category number 1 is going to be where n is even and a is greater than 0. So it's ax to the n. So I'm going to use a fairly basic example, which would be y equals x squared. A is 1, greater than 0, and n is even. All right. And basically, we have a graph that looks like this, right? We're all familiar with this graph. That's great. So basically what we can say here is that as x approaches negative infinity, which means that x is going, we're going this way, this way, this way, this way, this way. What now the question is, what's happening to the y value? It's going up, 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 up. So we would finish this by saying f of x approaches infinity. All right. On the other side, it's as x approaches infinity, f of x, right? And again, I'll do x goes larger, 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 larger. What's happening to the y value is the question. It's going up, 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 up. So x approaches infinity. And whenever this is your leading term, n is even, a is greater than 0, this is going to be your end behavior. All right, category number 2 is going to be when n is still even, but a is less than 0. And I'll give an example, would be y equals negative x squared. So if I made a quick graph, would look something like that, right? Graph doesn't have to be exact. It's more just a visual. So I can say as x approaches negative infinity, right? As x gets smaller, 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 what happens to the y value? Well, it goes down, 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 right? So we would finish this by saying f of x approaches negative infinity. Same on the other side, as x approaches infinity, right? We see the graph goes down. F of x approaches negative infinity. And again, same thing. Whenever your leading term fits these criteria, all right, in the second category, this will be your answer. All right. Now the third category, now we change. We have a, we can go back to a is greater than 0. A is greater than a. Nope. A is greater than 0. And n is odd. So I'm going to have y equals x cubed. And I'll sketch a quick graph. It's going to kind of look like this. So as x approaches infinity, what happens to the y value? F of x approach, we see it goes up, 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 infinity. And as x approaches negative infinity, we see the y values go down, 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 down. So negative infinity. And the last one, not least, the fourth category is n is odd. A is less than 0. Y equals negative x cubed. So I'm going to sketch a quick graph for a nice visual. All right, so as x approaches infinity, you're looking at what f of x is doing, and it's going down, down, down. So you would answer negative infinity. And again, I would give you as x approaches negative infinity, you're looking at what f of x is doing, and it is going up, 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 up. So you would answer infinity. All right, and again, anytime your leading term fits this criteria, all right, you would fill out your end behavior in this way. All right, that's all I have for you for now. So thanks for listening. There's a lot more practice ahead, but I hope I gave you a good start. See you soon.